Welcome to the preparation videos of the course Mathematical Foundations in Software Engineering. This is the second video in the series on statistics and probability. We will now continue to talk about the concept of probability. Why would you need to learn probability theory? Well, probability theory is the logic of science. In particular, it's a critical component of inductive logic. Whenever human beings are dealing with probabilistic reasoning, we have a tendency to fall into traps. We call it probability blindness. Probability blindness is the human brain's observed inability to make intuitive estimates of the probability of an event, even when presented with all of the relevant evidence. As an example, you decide to get tested. And suppose that the testing methods for this disease are correct 99% of the time. In other words, if you have the disease, it shows that you do with 99% probability. And if you don't have the disease, it shows that you do not with 99% probability. Suppose this disease is actually quite rare, occurring randomly in the general population in only 1 of every 10,000 people. If your test results come back positive, what are your chances that you actually have the disease? Do you think it is approximately 0.99, 0.90, 0.1, or 0.01? The answer is less than 0.01. That is, there is less than 1% chance that you actually have the disease. Doesn't feel right, does it? We will in this video show you how to calculate probabilities, such as these, using the logic of science, that is, probability theory. Let's start with a game example. Suppose you are invited to play a game of blindly picking marbles from an urn. You bet $3.50 to play and you win $10 if you pick 2 golden marbles in a row. Now, what are the odds of winning? Given this game setup, thought, we will later return to it. Now, what do we mean by probability? It's about the likelihood of an event to occur. If an event is unlikely to occur, the probability is low. And of course, if an event is likely to occur, we speak of a high probability. We can assign numerical values to probability. If an event A is unlikely to occur, probability P of A has a low value. The event getting hit by lightning is a classical example that has a probability value close to 0. If it's totally impossible that an event will occur, probability is 0. On the other hand, if an event A is likely to occur, probability is closer to 1. For example, the event arriving safely when traveling by airplane has a probability value very, very close to 1. Or as my uncle usually says, no one has ever stayed up there forever. And if an event is absolutely certain to occur, probability is 1. Here's the urn and marbles example again. What's the probability of picking a golden marble? There are 3 golden marbles and 2 black marbles, 5 marbles in total. Of course, we immediately see there's 3 in 5 chance here. But how do we express this more formally? First, let's define the simple event, A1, as picking golden marble 1. A simple event is a single outcome. In the same way, let's define the simple events A2 and A3 as picking golden marble 2 and 3 respectively. For completeness, let's also define the simple events B1 and B2 as picking black marble 1 and 2 respectively. In this game, we are not in for picking a particular golden marble. Any golden marble will do. Therefore, we define the event A as picking any golden marble. Now that event A is the collection or the set of the simple events A1, A2, and A3. We also need to define the sample space S as all possible outcomes, or any marble. In this case, in other words, the sample space is the collection or the set of all simple events. Now, the probability P of event A to occur is the number of elements in A divided by the number of elements in S, 3 divided by 5. Let us next look into combining probabilities using the addition rules for probabilities. The addition rule helps you solve probability problems that involve 2 events. Let's have a look at the same example again. We already know the probability of picking any golden marble. It's 3 over 5. We denote it P of A. What's the probability of the event picking any marble marked 1? Of course, it's 2 over 5, since we have 2 marbles marked 1. Let's denote this P of C. Now, what's the probability of picking any golden marble? P of A, or any marble marked 1, P of C. We use the union symbol to write this expression. Can we simply add the probabilities for the 2 events? No, that can't be correct. The sum adds to a probability of 1. Let's have a look again. We have 3 golden marbles. The set is highlighted in red. We have 2 marbles marked 1. The set is highlighted in blue. We notice that the golden marble marked 1 is a member of both sets. It's the intersection set. If we just add the sets, the probability of picking this marble is incorrectly counted twice, so to speak. We have to subtract the intersection to get it right. Let's consider the probability of some other events. What's the probability of picking any black marble, or the marble marked 3? In this case, there's no intersection set, which means that the probabilities for the individual events actually can be added. The events are said to be mutually exclusive if the probability for the intersection is 0. Before moving on, I must introduce complementary events. It's quite simple, yet a very useful property when solving probability problems. A complementary event is the event of it not occurring. If the original event is denoted A, the complementary event is simply not event A. In our Urn and Marbles example, the complementary event is not picking any golden marble, which of course equals any black marble. But more interestingly, the probability of the complementary event to occur is 1 minus the probability of the event itself to occur. Again, all this might seem simple and obvious, but in many cases it's really effective to involve complementary events when solving problems. And please note, the complementary event and the event itself must be mutually exclusive for this to hold true. In this case, it works since events A and B are mutually exclusive. There are no overlapping sets. A marble is either golden or black.